Um, so who knows anything about resampling? Yeah, you know quite a bit. You seem very confident in your.
Pretty sure I've used it.
You're pretty sure.
Yeah. Well, I had to do like network resampling to test something,
Ah, okay.
but it's the same idea of data. Also, if you want to do significance testing, it's a little bit more like it's really test to see which data is the same kind of thing.
Yeah, that's good. So there are like a number of techniques for resampling. Resampling is kind of just from the word resampling. So in statistics, there's the so-called unknown population characteristics, and then you take samples from that population that hopefully are representative of that of the population, and then you infer the characteristics of that population of the sample based on the population. But it's always either too costly or like too labor intensive to actually know the true population characteristics, so you always use samples. Now with resampling, so with the sample, you take the sample to be able to estimate certain characteristics of that sample in a way that allows you to find out the certainty, or I guess uncertainty, of whatever you're measuring. So like, let's say we want to find the mean of height in this sample. You can do the simple thing. So I guess just as a warning, who here is like likes stats? Okay, so, okay. Who here is fairly familiar with some stats? Who here is really scared to death of stats? Stats can be kind of scary, especially the way they're sometimes taught. They're not always taught in the most friendly way. But, so just as a warning, I'm just going to cover a little bit of some stats. And so if we were to think of like the mean is, who here knows what the mean, how to calculate the mean? Yes? Anybody want to say? What's the formula?
Sum of raw samples divided by number of samples.
Yeah, there you go, yeah. I don't know how to actually write this in, but yeah. Sum of samples divided by number of samples. So that's something like that's fairly simple. You find out what the average is of the population. So for example, height. So we take a sample from a population and we find out the height, the average height of that sample. And so then we say, okay, let's say just around here, it's maybe like 5 and 8 inches average. Who's the tallest? What?
Probably me. Well, I was over here. 6 on the dot. I'm 6.
Okay, so who's I'm assuming you're the shortest. Yeah. How much?
Under 5.
Under 5. Okay, so yeah, so that would probably be like 5.5 feet would be the average. And then if we were to compare, then we'd make, like, let's pretend like we're like a representative sample of the population. So we'd say we're actually, so that the mean of the population is about 5.5. But we know that because this is just a sample, we could have easily just gone to another classroom of the sample divided by the number of the sample. So in R, that would be something like square root, var, we'll do 1 to 10. Doing, what is it? Pretty sure that's right. Well, there's a standard deviation. Is that right? That's the variance, the square root of the variance of the sample divided by the number of the sample. That's a, yeah, of all of that. Yeah, yeah. So the square root of the entire thing. Yeah, yeah. Okay. So a problem with this is that the uncertainty is based on the sample itself, right? It's not the uncertainty of how many of the actual measures of the mean. So one way of identifying the actual precision of the statistic is by using resampling. And so let's take, let's do, so what this does, this is just something I'm going to be working with for a little while. What run if does is it just generates 10 random numbers between 0 and 1. So you can see here that these are kind of like just all sort of random. Now, first, I guess I'll just do this. The first technique that I'm going to be talking about is called bootstrap. So this is bootstrap is a way of resampling for finding out the uncertainty of usually just univariate, so just a single measure. So in this case, height. So it has nothing to do with another variable. So like, oh really? Oh, I wonder if I. Oh. Yeah, my internet might have. What? Do you want me to try to click screen share again? Is it working? Okay. So with Bootstrap, you resample this, but instead of taking so instead of taking, there's two ways of doing resampling. You just simply take the order of the sample and just rearrange it. So this plays a role later on. What I'm going to be talking about, it's called permutation testing. I'm not going to talk about it right now. Right now it's just bootstrapping. So with bootstrapping, what it does is it takes a sample of this and chooses 10 numbers from this. Now, because there's 10 numbers, it's going to choose like all of them, right? But if you say that each of these numbers has an equal chance of being chosen, you have potential for some of these measures some of these values to be taken twice or 3 times, right? So this is called what's known as with replacement. So you resample with replacement. So in this case, let's say we just want to see, just to look at the distribution of X. So we can see that the distribution of X is kind of like, there's some values that are missing, and it's kind of just fairly evenly distributed between 0 and 0.8. And then if we look at the mean of that, it's 0.4, so kind of like right in the middle, right? Which that's kind of what we assume, that's what it means. Now with bootstrapping, if we wanted to find out how certain we are of that mean, we do, so it's sample x is true. So this is the code that you use to be able to resample x, the number of values. You have to indicate here replace equals true to say that you want to be able to have equal each value have equal chance to be chosen. So you can see here there's actually 1, 2, 3 of the 4 of the same values, right? So then if you were to take the mean of this, but that's okay. So the mean is now slightly different from before. If you remember, the mean was previously 46, but now it's 47. So we could keep doing that, keep resampling. So if I were to run this again, now it's slightly different. Take the mean again, it's slightly different. We can keep on doing that, and as you do that more times, you can start to get a distribution of where the mean is from that sample, and then you can estimate the uncertainty of that mean directly. So before it's based on the data, and now you're you're finding out the distribution of all the possible means there are, and then finding out what the range of those means are. And then that allows you to be able to make a more informed guess about what the mean is of the population. Okay, so just to illustrate, so we're going to load up dplyr. Hope everybody has these packages. ggplot2. I'm going to create a data frame. Both 10. Group by num. Mutate means equals mean sample x is true. Okay. So. Gonna make it a little bit bigger here. Okay. So basically what I've done here, I'll talk about the code first and then I'll show you. So all I'm saying is I want to resample X and then take the mean of that resample 10 times. And then I'm going to plot what that's the distribution so far of the means and see how the means distribute. And I'm only doing it 10 times, so there's only 10 samples being taken. So we wouldn't expect there to be too much, we would expect there to be more differences with the means because it's only 10 times they were taking a sample. So when you look at the distribution, it's kind of going all over the place, right? Like there's some means over here, there's some means over there, there's a couple more means over here, but it's kind of just all over the place. Now, what if we do that instead of 10 times, we do that 100 times. Start to see it's starting to form a shape, right? Certain means are starting to cluster around a certain value. When you do that again, let's do 1,000 times this time. And again, you can start to see that as you do more and more resampling, the means start to cluster, most of the means start to cluster around a certain range. And so from this range, then you can calculate how uncertain you are of what the actual mean is of the population.
Why doesn't the standard error just tell you that?
Because the standard error is based off of the data itself, the variance of the data. But with the resampling, you can actually calculate all possible values of the means, at least based on the sample. But assuming like that you have a fairly equal, how do you say, this bootstrapping is more useful when you have a smaller sample size, because as you get a bigger sample size, like let's say you take a population of 1,000 people, and then you calculate the means of height. The mean of the 1,000 people height and the standard error that you can calculate from that is going to be more closer to the population than if you were to just take 10 people, because there's only 10 people, right? There's more variability in choosing 10 people and their heights. So this is really more important when you have smaller sample sizes rather than bigger sample sizes, because both the standard error and the bootstrap standard confidence interval will be fairly similar with bigger sample sizes, if that kind of makes sense.
How about the measure mean that's close to the true mean?
Sorry?
The mean that you get in your sample is close to the true mean, or more likely close to the true mean.
Yes, the bigger the sample size. So the bigger the sample size, the less likely you need to do statistics on it. Because statistics are to help you identify whether or not the sample is representative of the population. That's why if you have data on the entire population, you don't need to do stats at all. Okay, so this is sort of to illustrate the point of resampling, but in R, there is a package called boot, which does this all kind of for you. So boot has a function called boot. I think it's called boot. Yes. And it takes the data, and then it takes a function that calculates a statistic. So in this case, we have to have that function. So I'm going to create a function for, I'll explain what this means in a second. Okay. So what this is doing is you're, of course, loading up the boot package and then creating a function that calculates the mean, and it takes the values and then it takes the resampling of the values. And so you want to be able to calculate the mean of that resample, and then you use this function inside the boot function from the boot package. And so you take the values, you apply this boot, and then you calculate and then this is how many times you do resample. So in this case, it's 1,000 times of resample. Just like before, except this is one line of code, and it also gives you some additional information. You can do like 1,000, 2,000, however many you want to do. And so it gives you just some information So there's like the original mean. This is the original mean. If you were to just run mean on the values. Bias is how different the bootstrapped mean is from the original mean. So in this case, it's pretty tiny. And then it calculates the actual standard error. You can also calculate, so if we do, okay. Just put the mean inside. We can. Good question. Okay, so x of I, or like this is indexing. Who's? I guess I should ask. Who's really familiar with R? Okay. And then everybody else. Okay, so, and then what about Python? Okay. Anything else? Any other languages? What language do you use?
I'm okay with R, not an expert. Around and like shuttles.
Okay. I can't make any analogies to those because I don't know those languages, but so this is just like indexing in Python. And so the I here is just saying what the resampling will be of x. So x is just the values that you give it. So it could be any like vector of values. And then it's saying from those samples, I want to select certain position, certain that sample. So like let's pretend like if you could get a resample where let's say it's only 10, there's only 10 values within the vector. And the I says, I want to take the first value of x, of the vector, 10 times. So you have 10 values that are exactly the same. That's what I is saying.
So I is a random number?
I is a random number. A random number of from 1 to the size of this.
Well, so X, I number, right?
Xi is a vector. So it'll be a x. So I can
You should like X bracket.
I'll show you an example here. So x, let's just say, so we know x is this, right? x1 is that first value. And then if we do c, x, c1 to 3, it's going to be the first 3. Now if we do c1, 1,
So I is a vector as well.
I is a vector as well. Yeah, sorry, I is a vector of from, it just tells what values to take from the original. Yes, it's a vector of size 10. Both of them are size 10, but the values are different. So I would just be from anywhere from 1 to 10 randomly. Does that make sense? We got to keep that in mind. Forget about that. So the reason why you need to provide boot with these two values is because boot will put in that random numbers in here to be able to calculate the mean from that value.
R is the number of files.
Yes, number of replications or number of resampling, or I think they call it replications. So you can calculate the confidence interval using boot.ci. And then it gives you several different So this is assuming a normal distribution. I don't know what basic is. And then this one is like Bayesian something. Anyway, this one is the one that they recommend to use. So this would be the actual uncertainty of the mean. You can also use it for anything. So you can do the same thing for median. It does the same thing. If you wanted to get a little bit more complicated, you can also do, for instance, like a correlation of two values. Oh, I should mention here, if you want a little bit of a tidier version of this, you can do library broom and then tidy. And then it outputs it as a data frame. So it's a little bit easier to work with later on. This is quite a nifty package. Okay, so if we have, in this case, we have to create, so if we do a correlation, that's like two values correlated on each other. So you need to have two values. Again. Let's call it DS. Easier to type. So that's a correlation between these two values. Does it? Who knows what correlation is? Okay, most of you. Does somebody want to quickly explain it?
It would be like the relationship between your data, right? So the more alike they are, the more information there is, right? So then they try to do like your regression, right? You try to get features around like so correlated, right? Then they say that you want to show some slides.
Good way, yeah. It's if you want to visualize it here, it's just assuming it's kind of creating a line through this. So in this case, the values are kind of all over the place, but at 0.4, so that means that, I mean, it doesn't say exactly where the line is, but it means that they're fairly correlated, not too much. 0.4 is fairly low.
Pretty good for.
Yeah, it is pretty good for anywhere. Sorry? So if we want to do it using the bootstrap. So in this case, we do core boot core function data and I core data x I data. So in this case, unfortunately, you can't, you have to know what the values are beforehand. So like this is the column, so $, just is saying take the X the X variable from the data, from this data set, and select these random values from that column. And then this is saying Y from that data set. So Y, yeah.
Is it choose the same unit, indices for X and Y? So it's in
Yes.
better indices.
Yes, it does, yeah. And in fact, I'll show you a little graphic here. It's in but the bootstrap, when there's two, is just, I can't really see the colors. That's too bad. So this is supposed to be like red and blue or something like that. So you just imagine, yeah, it's not very good projected. Oh, you guys can see it?
Yes, or does
Okay. I can't see it at all. It looks all white. I'm a little colorblind, so that makes it challenging. Okay, so I'm just going to assume that I'm pointing at the right things here. So assuming like this is red. Wait, what color is this?
Red.
Yeah, okay. And then this is like light blue or something. Okay. In this case, it's resampling and choosing all reds and blues. This is really bad. Maybe no, this isn't great. But so essentially it keeps the same pairs together, right? The values are always together. So you're taking the bootstrap takes it exactly from the original, but keeps the pairs together. I'll come back to these other ones in a second. I'll come back to this in a second. Okay, so if we do boot ds, and then boot core, r equals 1000. Oops. So you can kind of see here, the syntax is the same, like no matter what. It's just the only thing that changes is the function inside. So it has like a consistent way of working. You just have to change that function, which is kind of nice. And so here this is the original correlation. The bias would be how different that the bootstrap correlation is from the original. So in this case, it's 0.06, which isn't too off. And then it calculates a standard error. And then if we do, so cores, boot.ci, cores, it again calculates it calculates the confidence interval. So you can see here that this is quite a wide confidence interval. What that's meaning is like, I generated 10 random numbers. So you wouldn't assume that it's going to be reflective real. So because of that, you can see here that the distribution is quite wide. This is like almost saying that there is no correlation, which we would assume because they're random numbers. So that's essentially bootstrap. And it's useful for individual like predictors or for estimating confidence intervals.
Can you compare that to the, because like when you run a linear regression, you also get an incentive from that.
Yes.
So is that, like, how does that number compare to the confidence interval?
So linear regression is just a little bit different. You can run bootstrapping on linear regression, but in the case of linear regression, it's better to do cross-validation of a kind of.
No, well, I guess I'm curious, like, if you like print out what the uncertainty on the slope is
Yes.
in linear regression,
Yes.
will it also be like centered around 0 and like fairly wide? And you can see what I'm asking.
Well, for linear regression or for just in general
Like
anything?
this, when you calculate what the R value is,
Yeah.
you do linear regression.
Yeah, true. Yeah.
And
Only for two variables.
only for 2 variables.
Yeah, yeah.
But in that regression, you you didn't show it, but you got some slope value, and there's some uncertainty about for the slope, but you didn't show it. But that's like not the bootstraps value. That's just like what came out of the regression. So I'm curious how that.
Well,
compares
I mean,
to-
let's find out. Y is as a function of x, data equals ds. Ah. So this is the uncertainty around this. Oh, I guess I have to. 1 second. Actually, I need to scale these first. So standard error in this case is, or no, wait, sorry. It's better to use this. So the confidence interval is, it's close and it's actually wider than the bootstrapped, but it's relatively similar, except it goes past 1, which in correlation, that's not. I don't think I did this exactly properly, but this should be fine.
It's a different measurement, right? Correlation and regression.
Yeah. Yeah, that's true, except when you only have 2 values, and so scale is just mean centering and having 1 standard deviation on each side. When you scale the y and you scale the x, the formula is exactly the same thing as a correlation. So the values should be exact. And in fact, you can see here, the estimate is 0.4 and the correlation is 0.4. So they're exactly the same. You can do the math, like it comes out to be exactly the same when you scale it, but the key is to scale it.
So the scale.
The scale is just make sure that the mean is 0 and there's the standard deviation is equal to 1 on each side.
So do I always expect bootstrapping to give me a smaller uncertainty than doing like the standard error?
I don't know, that's a good question. You'd probably get a more reliable estimate. So because the problem with the confidence interval here is that it's based on the standard error, which is calculated based on the data, and then only and then calculating it from like the 95%, so like probability. So the difference between this is that you're using the p-value versus the bootstrapping, which you're actually empirically calculating the distribution or the confidence interval. Do you know?
Yeah, I understand the difference, and you like just haven't convinced me yet that bootstrapping is somehow more representative of the underlying population.
Like using Bootstrap really depends on the research question. Like for my purposes, I don't use Bootstrap. There's no point. Like because what I'm looking at is more, I guess, biological and kind of well defined. Like I kind of already know the answer, so I don't really need to know But if your research question is kind of out there or there's not a whole lot done already, doing the bootstrap would just give you maybe a better estimate than if you were just to do the standard, especially if your sample size is small.
Let's go back to the.
Yeah. I mean, there's a lot of reasons why you might want to use it, why you might not use it. Okay.
Complicated, and you don't really know how the errors are going to play out. So you just, it's not like mean triangulation, it's like something like you're trying to simulate an experiment and like input goes to output goes to input, you just have this error and it's kind of what you're trying to do it.
It definitely is more of like a niche case. Okay, so the next thing is called permutation testing. Oops. So we'll go back to this figure here. So while bootstrapping is good for individual like variables and finding out the uncertainty of the mean of that or the uncertainty of those, permutation is mainly used for testing hypotheses because so in this case, again, I can't really see, but so bootstrap keeps the rows the same, but then permutation changes in this case, the y variable. So you change the location of the y variable and moves it all up so that when you do run, for instance, a correlation or linear regression, or more likely this is done in like in cases of ANOVA when there's like for instance sex or right-handedness or something like that, where it's either yes or no or a couple of categories. By replacing all the possible combinations of the predictor with the x with the y, you can find out the distribution of what the null hypothesis would be, and then based on your actual sample, you can find out how that is different from the null hypothesis based on permutations. So again, it gets more precise estimate of how likely what you're seeing is true versus not true. And again, it doesn't rely on p-values because, well, p-values are not too reliable. Okay, so if we create, again, another data set, actually, we can reuse the data set in this case. So there's two values. And again, I'm going to do the correlation again. Put simply in this case, I didn't put replace equals true. So you're reshuffling the order between these x and y variables, but without replacement. So you keep, so they're all you're doing is just changing the order of the values. So like, so this, originally this goes with this, but in this case, this goes with this compared to, now this is in the second position. So just the order has been changed. And then if you were to run, so if you were to do a correlation on correlation of so the original correlation is 0.4, and then the next correlation is minus 0.06, which makes sense because we changed all the values around. And if we do as before, we do data frame equals 1 to, let's say 1,000, or 1 to 100. By Hit core. I'm going to use Spearman. Okay, just to explain a little bit. I'm using Spearman because I'm going to be showing an example later from another package called Coin that doesn't have, that only has a Spearman correlation. So I just want to keep it consistent. And so what I'm doing here is, again, I'm resampling 100 times and taking the correlation each of those 100 times, and then just plotting what the resulting 100 correlations are. So again, as before, you can kind of start to see like a little bit of a distribution here going on. And then if we were to do 1,000, it starts to get closer to correlation of 0. Now this would make sense because the values that we generated were, again, random, so we wouldn't assume there to be a correlation, so it kind of consistently goes around 0. This is particularly useful with, as I said, with non-continuous variables. So like if you have binary or categorical. So the package to use this would be Coin. We can use, there's a thing called Spearman test Y. So then in this case, so the usefulness of this, the usefulness of using Coin, which is the equivalent of the permutation test, is that it calculates an actual p-value rather than a p-value based on sheets, if that makes sense. Like the p-value, so when you run a correlation and you calculate the p-value, you're comparing to, has anybody ever taken a stats course where they actually should give you a sheet of all the p-values? Has anybody? Yeah. So that's where the p-values come from. They're kind of pre-generated values that correspond to certain probabilities. You're directly calculating the p-value. So rather than basing it on some other, I don't know how else to say it, a shoddy measure, like a shoddy measure, p-values is shoddy, you're actually calculating something that's based on the how do you say this? I guess empirically calculated. Does anybody know a better word for this?
I think people use that empirical p-value.
Yeah, empirical p-value, yeah. So it's like an actual calculated p-value versus something that's just compared to the sheets.
Are you saying like you're not assuming something about the distribution?
Yes, that's a good way of saying it. Yes. So the value of the permutation testing is that you're not, it's robust to different types of distributions. So you're calculating the actual distribution and then comparing it to that distribution. So there's less, it's a little bit more robust to specific assumptions about the distribution of the data point. So it doesn't have to be normal or whatever, if that makes any sense. Like the Gaussian. Is that how you say it? Gaussian? Yes. And there's a bunch of other commands in here. So if you do coin chi-squared tests, there's trying to find it. I think there was like an ANOVA one in here somewhere. I can't find it. Anyway, if you ever heard the term exact, this is kind of, when the test is considered exact, this is what is kind of going on underneath. I don't know why they call that exact, but there it is. And I don't really have anything else. Any questions? Any other questions? No? Yeah.
Any